Start, sir.
Get started.
Yes, sir.
And one more thing, do I have to keep my video on all the time?
Yes, sir.
Okay. Yes, sir.
So you have to mute the YouTube, sir. YouTube video when it starts playing.
And one more thing, do I have to keep my video on all the time? Yes, sir. Okay. Yes, sir. So you have to mute the YouTube, sir. YouTube video when it starts playing. One more thing, do I have to... Okay, so I have muted the YouTube video. So
Yes,
let's go to...
You can start the session now, sir.
All right. So first of all, good evening, all the participants to the live session of integral and vector calculus. I have some questions that I received in the response sheet. So the first one is about our exam question pattern. Okay, so the exam question pattern, as far as I remember, it will be so it's if I remember correctly, it will be either MCQ type, so multiple choice questions. So there will be 4 options. You have to choose whichever is correct. Then it can be also MSQ type. That means there can be more than one correct answer, which you have to choose. There can be true false. So you have to choose whether a certain statement or a example, or I mean, mostly they are examples, is true or false. So true false type, maybe fill in the blanks type, but I'm not sure. So it is mostly mixture of all these how to say 4 types of question pattern. All right. Another response that I have got, it only mentions vector calculus. So I don't know what you mean by this because here nothing else is written. So if you have any Samyadeep Ghosh, if you have any specific question related to vector calculus, then please ask in the chat during this live session because here it only says vector calculus. And the third question that I have in this response sheet is from Harihara Mahama. It's about the geometrical interpretation of unit normal, unit binormal, osculating plane, normal plane, and rectifying plane. So first of all, I mean, this I have already tried to explain during the lecture itself. But if you would like me to explain it again. So first of all, in case of 3-dimensional geometry, so in case of 2-dimensional geometry, you don't have binormal, right? We basically have, in case of 2D, tangent and normal. So if you have any curve, you can draw the tangent, and you can also talk about the normal. But in case of 3-dimensional geometry, in 3D, basically, we talk about surfaces. And in case of surfaces, you can have tangent, you can have normal, and you can also have binormal. Okay, so this binormal is something that is perpendicular to both tangent and normal. So now you can see why I said there is no binormal in case of 2D. So in case of 2D, you cannot have another normal that will be perpendicular to both tangent and normal. So in case of 3-dimensional geometry, you have tangent, you have normal. So it may happen that your tangent and normal are in the same plane, and binormal is perpendicular to that plane. Or you can have normal and binormal in the same plane, and tangent is perpendicular to that plane. And you have binormal and tangent in the same plane, and normal is perpendicular to that plane. So either one of them must be perpendicular to the plane in which the two of them, I mean 2 out of 3, is contained, right? So now that we have introduced the definition, and that is why you have those relations, b equals to t cross n. That means binormal is given by cross product of tangent and normal. Similarly, tangent is given by the cross product of normal and binormal, and normal is given by the cross product of binormal and tangent. All right. So in a way, they form a right-handed screw system, b, n, and t. Now, that we have introduced the tangent and normal vectors, which are orthogonal to each other and lie in the osculating plane. So basically, the plane defined by the normal and binormal vectors are called the normal plane, and the plane defined by binormal and tangent vectors are called as rectifying plane. All right. So the plane that is defined by tangent and normal are called as osculating plane. So you have tangent and normal lying in the same plane, and if you can be able to write down the equation of the plane in which tangent and normal are present with the help of those tangent and normal, then that plane is called as osculating plane. Now, if you have tangent, if you have normal and binormal lying in a certain plane, and if you can be able to write down the equation of that plane, then that is called as normal plane. And finally, the plane which is defined by binormal and the tangent, that plane is called as rectifying plane. So osculating plane for tangent and normal vectors, normal plane for normal and binormal vectors, and rectifying plane for binormal and tangent vectors. So that's how the definition goes. All right. We in the lecture we have also derived the equation. So I hope from that example it would also make it clear for you what are these topics. All right. Let's see. Are there any questions so far? No. You're welcome. Yes, so I have another question from Mr. Aditya Ghosh about geometrical interpretation of directional derivative. So first of all, in case of um, one-dimensional geometry, so in case of a scalar function where you write y is equals to fx, where f is a function of one variable, there when you talk about derivative, you basically do total derivative like df dx. But the minute you go from 1D to 2D, so then in that case, what happens is it can no longer be your df dx, because now you basically have direction, you basically have x component and y component. So you write z equals to fxy. So we cannot really talk about df dx or df dy. Then it comes partial derivatives, del f del x, del f del y. And then we can define the total differential df as del f del x times dx plus del f del y times dy, which is the total differential, but that's not actually your df dx in a way. Okay, so in case of vectors, let's say in R3, when we talk about the derivative, the usual concept of derivative changes. And since you have a vector, we cannot have simply df dx or del f del x, right? We can, in case of vectors, we can always talk about in a way that nabla operator. So you are charging basically the nabla operator, whether you are charging on a scalar function or on a vector function, that depends. So if you're charging on a scalar function, then it's basically the gradient. And when you are charging on a vector function, now how you are charging that also depends whether it is a dot product or whether it is a cross product. Now, if it is a scalar function, and if you charge this gradient, so that means what you are doing is you are calculating component wise this del f del x I plus del f del y j plus del f del z k. So in a way, this is like a partial derivative with respect to each component. Now, if I say that calculate the partial derivative along a certain vector. So when you are calculating this three partial derivatives, del f, del x, del f, del y, del f, del z, along a certain vector, so along that direction, basically, we are saying that the derivative will be given by this certain number in a way. So that when we are, it's more or less like that projection definition. So when you take or the component, so you say component of this vector along this vector is basically a component of A along B is A dot B. Or when you calculate that projection, then it's A dot B by mod of B whole square or mod of B, something like that. So it's the same thing that you are calculating this gradient of F or the component of gradient of F along a certain vector. So when you're calculating the component of this gradient of F along a certain vector, that component is basically called as this directional derivative, right? And it is given by that formula gradient of f dot n. So sometimes we also then we also calculate that unit vector, and then we take gradient of f dot n, and we write the directional derivative. So it's in a rough sense, you can visualize it as calculating the component of that gradient of the function f along a certain vector, right? And that's how we write that gradient of f dot n is the directional derivative. Okay. You're welcome. Okay, please suggest a good book after completing vector calculus. Thomas calculus for undergraduate, vector calculus. Thomas calculus for undergraduate. Any good book for vector calculus? Actually, it is such a common topic for undergraduate studies that you can find several books that are available in the market that you can look into. Usually, what I would say is that this Advanced Engineering Mathematics by Krejcik, that one is very good. There you can find some say, examples as well, and it's a good reference book. But at the same time, if you're interested in more examples and how to say, and also theory as well, so you can look into any one of those books from publishers like Krishna Prakashan, then any this NCERT region publisher book. So there they usually solve a lot of examples because it's a very common topic and it's a very basic topic. So there has been a huge amount of books that has been written. So pick any one and just see whether the concepts explained there matching with the concepts that I have explained to you, and then you can solve some problems, maybe draw the graphs and the figures just to make it more convenient for you to understand. But for the time being, I don't have any particular suggestion about any books on vector calculus. So usually I prefer to look into Advanced Engineering Mathematics by Krejcik, but you can also look into some other books as well. Okay, so I can see, especially for theory purpose, yeah, for theory purpose, I think Krejcik book is fine. He does explain some theory as well. Thomas calculus is fine. I think, uh, what else? So let me see, what are the references that I have suggested? ETA, the integral vector calculus. Have I suggested any references? I think that's pretty much it. I mean, if you want to know some more books, so yeah, so for example, here I have mentioned vector analysis by Ghose and Maiti. Then there is another book, An Introduction to Vector Analysis for Physicists and Engineers by B. Haag. And another book is Vector Analysis by H.E. Newell Jr. So these are the three books that I can recommend. Let me tell you the name again. An Introduction to Vector Analysis for Physicists and Engineers by B. Hague, Hague. And there is another book, Vector Analysis by H.E. Newell, Newell, H.E. Newell. So these are the two books that you can look into where you can find some theory as well. I mean, so they are pretty much some standard books on vector calculus which you can look into. I think I can type in the chat. For me, it's possible. So let me just type the names of the books in the chat. So I have mentioned three books. You can look into these three books. So the first one is by an Indian author, so by the Indian author. So that would help you because they usually prefer to write in a simple language. And then you can look into the number 2 and number 3. Those are also good.
So you can end the session if there are no more questions.
Yeah, that's what I'm seeing. So if there are no further questions, then thank you. And I'm going to end the session now. Yes, so I will just leave the meeting.
Yes, sir.
Okay, thank you. What will happen to the YouTube?
I will end the session, sir.
Okay, thanks. Bye.